The intensity of a sound wave, or I, is proportional to the amplitude of that wave squared. So if you were to double the amplitude of a wave, you are going to quadruple the intensity here. Okay, and there's actually an equation where we can calculate this, where intensity is equal to power over the area that it's traveling through. Okay, so here is power, which will be in units of watts, if you remember from the energy chapter, and area that sound is traveling through in square meters. So intensity would have units of watts per square meter, and that's how we can calculate it. If we know the power, maybe wattage of the speakers, and the area where that sound is traveling through, then we can calculate the intensity in watts per square meter. If we think of just a quick example here, okay, if we have our source of sound here at the very center, and that's putting out sound in all directions. Let's say we want to know the intensity at this little point here. So we kind of consider this actually sphere around it, remember, because this is going to be in 3 dimensions. So this sphere around it would be the area that sound is traveling through. And so the intensity in this case, if we're just talking about, sort of a distance from that speaker, would be the power over the area of that sphere, and surface area of a sphere can be calculated by 4 pi r squared. So we plug that in for our area in this case. And r would be how far away we are from that speaker. So you can use r to represent a distance in that case to figure out how intense the sound is at a certain distance. However, because of the way our ear responds to sound, it's actually more convenient to talk about things in terms of decibel level. Decibel level is actually a logarithmic scale of intensity. So here's the equation, and then we'll give some examples of what it means. So the equation, we start with the Greek letter beta for decibels, 10 log of intensity over intensity naught. And intensity of naught represents the intensity of a sound at what we call our threshold of hearing, kind of the lowest intensity sound we can hear, which is 1 times 10 to the negative 12th watts per square meter. And so anytime you use this equation for intensity naught, you're just simply going to plug in this value, and this will calculate the decibel level of a sound for you, right? You might use maybe the previous equation to calculate an intensity, and then you could figure out decibels. So what we want to think about now is not necessarily this equation, but what does this logarithm thing mean, and how does it relate decibels to intensity? So let's make just a quick little chart here. And on one side we'll have our decibel level, and on the other side we'll have intensity. Because of the way logarithms work, if I take the logarithm of 1, that's 0. So if I have a decibel level of 0 decibels, that's going to be my 1 times 10 to the negative 12th watts per square meter, my threshold of hearing. If I go up to 10 decibels, so 10 decibels, that corresponds to an intensity of 1 times 10 to the negative 11th watts per square meter if we did the calculation. If I went up to 20 decibels, that would be 1 times 10 to the negative 10th watts per square meter. If I went up 30 decibels, to a value of 30 decibels, 1 times 10 to the negative 9th watts per square meter. So we should be able to start to pick out a pattern here. So we can say any increase in 10 decibels is not a 10 increase, but a power of 10 increase in intensity. So a change in 10 decibels is a 10 times change in intensity. And so that's the relationship when it comes to a logarithmic scale, is that a 10 times change over here results in just a value of 10 change here, or a value of 10 change here results in a 10 times the amount change on the right side of the equation. So now we're going to talk about the Doppler effect. This is something that we should be pretty familiar with. So what we want to start with is a source of sound. So we have our sound here, and our source of sound is going to be putting out a specific frequency. And we'll try and draw these as closely spaced or as evenly spaced as possible so that we get the idea here. So there's our source of sound putting out sound waves, and the Doppler effect is going to involve a relative motion, relative velocity between the source of sound and whatever is going to be our observer over here. So let's take our little person over here, and as this sound is standing still, let's have our person move towards the sound. So if our person is moving towards the sound, remember this sound is coming out at sort of regular intervals. But as this person is coming towards it, as he's moving towards it, he's going to hit these wave fronts faster than if he were just standing still, right? He's going to encounter them at a more frequent rate. So if he's moving towards that sound, he's actually going to hear an increase in frequency. Whereas the opposite thing, if you were standing here and moving away, right, he's moving in the same direction that the sound waves are moving, and so he's going to encounter them at a slower rate than he normally would, right? Because remember, these sound waves here are also moving this direction. So the result is the Doppler effect causes a shift in frequency. Okay, if things relative to each other are moving towards each other, then that's going to give us a higher frequency. And remember, that can be either the source or the observer. Okay, as long as relatively they're moving towards each other. And if they're moving away from each other, then that results in a lower frequency. Okay, you can hear this effect a lot. Probably the most common place you've heard it is with maybe a siren going down the street, right? As it comes towards you, it sounds like it has a high pitch, a high frequency. And as it moves away from you, it has a lower frequency or a lower pitch, right? Frequency and pitch are kind of the same thing. Another place you might hear Doppler a lot is on the news. If you're watching the weather, you hear about Doppler radar. Doppler radar, what it can do is tell us how quickly a storm is moving towards or away from us, tell us which direction it's going and how quickly, by knowing the frequency that it sends out and the frequency that it gets back and comparing those two frequencies. And if it gets back a frequency that's higher than what it sends out, then that means that the storm is moving towards the radar. And if it gets something that's lower than it sends out, then we know it's moving away from that radar. And so that's how they can tell which direction a storm is moving using Doppler radar.